LangGraph's vector store initialization establishes a semantic indexing layer for document retrieval, leveraging OpenAI's embedding model to transform textual chunks into high-dimensional vector representations. This foundational step enables efficient similarity search operations that will later power the retrieval agent's contextual reasoning capabilities. We're about to examine how the system instantiates an in-memory vector store from pre-processed document splits and configures a retriever interface, core components that bridge raw text data with the agent's decision-making pipeline.
From LangChain Core, vector stores import in-memory vector store. From LangChain OpenAI, import OpenAI embeddings. Vector store equals in-memory vector store from documents. Documents equals doc splits. Embedding equals OpenAI embeddings. Retriever equals vector store as retriever.
This code demonstrates the core pattern of creating an in-memory vector store for semantic search using OpenAI embeddings. The in-memory vector store from documents method takes pre-processed document chunks and converts them into vector representations using OpenAI embeddings, which is the standard approach for transforming text into dense vector spaces that capture semantic meaning. This is a lightweight, ephemeral solution suitable for development and testing, though production systems would typically use persistent vector stores like Pinecone or Weaviate. The retriever created via vector store as retriever provides the interface for semantic search operations. This two-step process, first embedding documents into a vector space, then creating a retrieval interface, is fundamental to RAG systems. The in-memory approach trades persistence for simplicity and speed during prototyping, while the OpenAI embeddings offer high-quality semantic representations out of the box. This pattern forms the foundation for the subsequent retrieval-augmented generation workflow in the tutorial. Let's break it down.
From LangChain Core, vector stores import in-memory vector store.
Imports the in-memory vector store class from LangChain's core vector stores module, providing an in-memory implementation for storing and retrieving vector embeddings.
From LangChain OpenAI, import OpenAI embeddings.
Imports the OpenAI embeddings class from the LangChain OpenAI module, which provides functionality for generating text embeddings using OpenAI's models.
Vector store equals in-memory vector store from documents.
Creates an in-memory vector store instance by loading and processing documents. The from documents class method handles the conversion of raw documents into vector embeddings and stores them in memory for efficient similarity search operations. The actual documents being processed aren't visible in this segment, but the method call indicates this is the initialization point for the vector storage system.
Documents equals doc splits. Embedding equals OpenAI embeddings.
Creates a vector store using the provided document splits and OpenAI embeddings. The documents parameter specifies the text chunks to be embedded, while embedding equals OpenAI embeddings initializes the embedding model that will convert these text chunks into numerical vectors for storage and retrieval.
Retriever equals vector store as retriever.
Converts the vector store into a retriever object, enabling query-based document retrieval functionality. The asRetriever method transforms the vector storage instance into a component that can fetch relevant documents based on similarity search or other retrieval criteria. This implementation establishes the semantic foundation for retrieval-augmented generation by combining OpenAI's embedding model with an in-memory vector store. The in-memory vector store from documents method handles the heavy lifting of converting document chunks into vector representations using OpenAI embeddings, creating a searchable semantic space. The subsequent asRetriever call then exposes this vector store as a queryable interface, completing the pipeline from raw text to retrieval-ready knowledge base. This two-step pattern, first embedding documents into a vector space, then creating a retrieval interface, is fundamental to RAG systems. The in-memory approach prioritizes development speed and simplicity, trading persistence for immediate feedback during prototyping, while maintaining the core semantic search capabilities that will power the agent's contextual reasoning.
The retriever breathes documents into vectors, then whispers back only the shadows that mirror the query.